Morning everyone, hope you guys are doing well. Just to give you a few extra days just study time before chapter 3 tests, we're just going to switch gears a little bit here. This is actually going to be the start of chapter 4. If you can start a fresh new page here in your notebooks. This one here is unit 4. It's talking about chemical bonding and chemical structure, one of my favorite chapters. So we've actually seen already a lot of this bonding. Since Science 9, Science 10, we learned about sort of two different extremes of bonding. On the one side, we have what's referred to as ionic bonding. On the other side, we have covalent bonding. Just for simplicity, we use terminology like, well, ionic, we're going to look for a metal and a non-metal. That's not wrong, although that's a little bit too simplistic of a definition. Covalent is similarly here a non-metal and a non-metal. That's one good way of tracking which one's which. We talk about what happens to the electrons here. In the ionic case here, we have electrons that are being transferred. Typically, the metal wants to lose the electron because it has a relatively large atomic radius, low ionization energy, whereas in the covalent case, because we're dealing with non-metals, their radii are very similar. They're not actually going to lose the tug-of-war as unevenly. So in this case here, we actually have an electron sharing sort of model. What I want to start introducing to you as we just start into this chapter is ionic and covalent are actually two ends of a spectrum. We can have compounds that are, say, 100% ionic or 100% covalent, but in actuality, the majority of our compounds will lie somewhere in between. We're going to have maybe a 80%, 20% ionic covalent ratio, or 30% covalent, 70% ionic sort of ratio. So we can actually be anywhere along the spectrum, which means we need to qualify this. Why isn't it metal, non-metal? What makes it more ionic or less ionic? We need to do this a little bit more detail. Remember the property we learned in chapter 3 that actually helps us figure out whether we're ionic or covalent was the property of electronegativity. So see if you can define electronegativity. So in this case here, it's the ability to attract electron pairs. You have to mention in a covalent bond. So basically what happens here is two elements, they run into each other here. X runs into Y. They can have any number of electrons. When they collide, it's going to be the valence shell on one that collides with the valence shell on the other. Usually it's going to be the unpaired electrons that do the bonding, and typically when a covalent bond, if it's going to form, typically it's going to be the unpaired electrons that do the bonding. So make sure you mention that notion it is in a bond. If these differences get to be too big, we will sort of fail from becoming covalent and we'll actually switch over to becoming ionic. So we'll have a look here. Let's say between X and Y, let's say we have fluorine against fluorine. Let's say the electronegativity is 4 and the electronegativity is 4. These numbers here are on your data booklet section 8, and although we're not necessarily comparing their absolute electronegativities, what we care is the difference. We care about the tug-of-war, is it even or uneven? So all we're going to do is we're going to go big number minus small number. In this case, 4 minus 4 is a perfect 0. This is the perfect case of sharing. And the sharing that I'm looking at here is a 50-50 sharing. You can either interpret that as the electrons are exactly halfway between the X and the Y, or a more accurate diagram is electrons are always moving. They're always swimming between X and Y. They're going to spend some time with X, and they're going to spend an equal time with Y. So 50-50, we're going to refer to this perfect case here as a non-polar. This is an even or equal sharing, so 50-50. So that's the 100% covalent case here. A lot of your non-metals, again, their tug-of-wars are fairly even. No one's going to really lose the electron. Let's compare it to another case of X and Y. So two different elements here. Just going to make up some numbers. Maybe somewhere downwards like cesium and them. Maybe they have an electronegativity of 1.0, whereas fluorine still has electronegativity of 4.0. Again, at first, I'm not really concerned with the absolute electronegativities. What I'm more concerned with here is the difference. So big number minus small number, 4 minus 3, just for simplicity, is a 3.0. What we have been throwing around is a number difference. When that difference gets to be somewhere close to 1.8, we'll flesh out that number in just a second here. But when it gets beyond 1.8, basically the stronger competitor, he's just tug-of-warring the electrons, but he's actually pulling so hard on this X here that instead of sharing the electrons in a covalent bond like we were supposed to, he actually completely snatches the electron to itself. At that point there, the X is out of luck. That's okay. having lost an electron, that's what metals want to do. They're going to revert down a shell. Typically, those inner shells are full, and then Y picks up that extra electron. We'll draw these Lewis structures more in the next lesson here, and only then do we get a full positive and a full negative charge. That's when we call it an ionic compound, right? So those are the two ends of the spectrum. That means we actually have a region between a difference of 0 to a difference of 1.8 where we can actually have slightly uneven sharing. In the ionic case here, we have 0, 100. There's no sharing at all. But what if we were like on the 1.7, 1.6? We're still kind of covalent, but leaning towards the ionic side. So what that would imply here is we have an X and a Y. I'm just going to make up some electronegativities again. Let's say the Y is still fluorine, and let's say the X here happens this time to be 2.8. You can try to find a metal in section 8 here that obeys that. First thing they have to do is they have to collide. They potentially could share electrons. What we're interested in studying here is the delta En, the difference in electronegativity. So I go big number minus small number. This time the difference is 1.2, and it's in favor of the Y side. It's not big enough to be 1.8, so it's not big enough for the electron to completely go to Y side, but these two electrons here, they do spend more time with the Y. We say electrons swish and swash. They swash more to the Y side, or better yet, you can even say the electrons are closer to the Y, although the X hasn't completely lost the electrons yet. So there's a slight imbalance. There's a separation of charge. What's happening here is because there's more electron density on the Y side, we've created what's called a dipole. A dipole represents this charge separation. We point towards the winner. We point towards the negative side. This side becomes kind of negative. I'm using a partial negative symbol. This side is kind of positive. Because we needed the full transfer for even a positive one and a full negative one, what we're talking about here is a fractional. So maybe this is like negative 0.2, or this one here is like positive 0.8, something like that. So some fractional, some decimal charge. It's a slight imbalance, and it points towards the winner for the dipole. In that case there, the sharing that I'm referring to here, the electronegativity difference is 1.2 like we said. Instead of a 50-50 split, maybe we have like a 70-30 kind of split. Oh, sorry, the other way around. So 70 on this side here and 30 on this side here. It's still sharing, so we can still refer to this as covalent, but it's a sharing that actually has poles to it, that actually has ends to the molecule. Because it has ends to the molecule, we can refer to this bond here as now called a covalent polar, or polar covalent. It's a covalent bond which has a positive side, a positive pole, and a negative pole to it. This does relate later on to whether molecules are polar or not, but just to show you, we are technically covalent, but it's slightly imbalanced, it's slightly in favor of the winner, slightly in favor of the Y side. Just wanted to flesh out a little bit more with you here. Why can't I just say always 1.8? Your data booklet here, this actually comes out of your option A. We're actually not going to do this option, but it does give us a nice diagram to refer to. And they refer to this one here as the Van Arkel-Ketelaar triangular bonding diagram. And what it basically does here is it plots another axis for us here. It plots delta En like we would do normally. We just said delta En of 0 is perfectly even sharing. 1.8, right? I just matched up. That's where my 1.8 shows up. It plots the En difference here, but it plots it against an average electronegativity. This is the only time I've actually seen this average electronegativity. It's just getting you to think about another axis for bonding. I'll show you what I mean here. If it truly was, let's say, fluorine fighting against fluorine. Right. So again, you check your section 8. It gives you a periodic table. It gives you electronegativity values. The electronegativity of fluorine is the highest. It's a 4.0 and a 4.0. If I just looked at the difference in electronegativity, big number minus small number, I'd say 0. That would put me along the 0 line. Down the 0 line, I notice on this triangular bonding diagram, I'm either metallic or I'm either covalent. What this axis shows me here is the average of my electronegativities. So looking once more at your exact numbers themselves, well, my average, 4 plus 4 divided by 2, is an average of 4. If I'm relatively high, that means the absolute electronegativities are actually higher as well, and I also have a difference of 0. That puts me directly in the covalent region. When would I be in, say, the metallic region? Let's say instead of fluorine and fluorine, let's say I put Na colliding with Na. In this case here, we would actually refer to this as metallic bonding in a second here. But what's going to happen is the Na has way lower electronegativity. Again, I don't have the numbers off the top of my head. I'm just going to make up a number here, or maybe I'll just look it up. Not be lazy, Mr. Young. So sodium here, obviously if it would work for me. Sodium electronegativity is a 0.9. That's what I was going to guess it was. 0.9 and 0.9. If you just consider the difference, big number minus small number, the difference is similarly 0. Both the fluorines are 0 and the sodiums are 0. And yet you wouldn't call sodium-sodium covalent. You would rather call them metallic. So one way of plotting it is you can actually plot, let's have another look at the absolute electronegativities. The absolute electronegativities is 0.9. I'm nowhere close to the 4. That's the average, right? 1 plus the other divided by 2. I'm at an average of about a 0.9. If I have a difference of 0, that puts me instead in the metallic region as well. So that's why this 1.8 here isn't perfect. The 1.8 becomes a nice dividing line because the majority of compounds we're going to deal with are going to be roughly about this average absolute electronegativity. But depending on the real average electronegativity, sometimes the crossover happens earlier than 1.8, sometimes it happens later than 1.8. That's why it's a little bit of a fluffy number. Right? So there's metallic, there's covalent, but nonetheless, we go from a non-polar covalent, a perfectly even sharing, there's a bunch of uneven sharing, which is called polar covalent, and then we have no sharing at all. We have the transfer case here. Typically, metals have low electronegativities, non-metals have high ones, so when you do the tug-of-war, it gets very, very uneven, so therefore we end up with this transfer case. So with that diagram, I just want to finish off this lesson here just looking at the 3 different types of bonding. We will look at metallic first because this one here relates to a little bit of chapter 3 stuff. We're going to have another look at ionic compounds and forming lattices, and then we'll form covalent. We'll spend another lesson later on talking about polar covalent and other applications of it. Right? So this is just a quick intro to bonding here. We'll start off with metallic bonding. So this was very important when we were defining melting point trends in chapter 3 here. Metallic bonding is electrostatic attraction or Coulomb attractions. Electrostatic attractions between, whenever we do a Coulomb, we think KQQ over R squared. It's between things that are positive. For this metallic bonding, the positive bit are the positive centers, the positive nuclei, and we have that funny language here of delocalized electrons again. So if you imagine with me here, someone hands you a block of sodium. So I would imagine sodium, 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 sodium. Right? The difference here is there are no nonmetals. They're definitely not ionic bonded. Because there are no nonmetals, there's no electron transfer, there's no Na+. The Nas here are all neutral Nas. So if I am going to do a Coulomb attraction, if I am going to try F is KQQ over R squared, I need to figure out who's the positive and who's the negative. In this case here, the positive are the positive nuclei. The positive centers are all these ones, and the solid state, they're sort of vibrating in place, but they're sort of stapled down. They can't really move. Every metal was supposed to have its own electrons. But fortunately for us here, metals, I'll write this down for you here. Since metals have larger radii on each period, should be able to quote here, low Z effective for that reason. That means metals have a combination. They have relatively low ionization and a low electronegativity, low electron affinity. So the low ionization energy part says it's really easy to remove an electron. You give it a quick nudge and that electron bumps right off. In terms of electronegativity and electron affinity, this is the ability for you to attract or gain those electrons back. Once those electrons are lost, it's really hard, my pen would work here, hard to regain. It's hard to capture that electron back. So electrons feel really unloved in this situation, although on average, every sodium should have that one valence electron. In fact, all its electrons, these electrons are free to actually roam around the entire bulk sample, which later on we're going to see makes it conductive because we have charges that can move. We refer to that as delocalized electrons. So there's the positive, there's the negative. The thing that's holding metals together in the solid state here is the positive nuclei are still attracted, even though the electrons are just loose and they're just swimming around. There is going to be some attraction from each of these sodium centers, each of these positive centers to the electrons that are just swimming around. We refer to this as the Electron Sea model. So between the positive nuclei and the negatives that are like a pool just swimming back and forth. Evidently here we see the proportional relationship. The bigger the charges, the stronger the force, as well as the smaller radius, the stronger the force. So back in chapter 3, we had said this type of bonding, metallic bonding, is stronger with more charges. So that can be in the line of having more protons when I walk across the periodic table. It could even be higher oxidation state in some cases. So higher charges being a +3 instead of a +2, and smaller radii. So if I have higher Z effective, if I go to the right on the periodic table, or if I have less shells, that's when metallic bonding gets stronger. That's why we saw with our melting point trend, the melting point generally increase as you headed towards the middle of the table. So that's all there is to sort of metallic bonding here. I wanted to emphasize metallic bonding is not ionic. We just have metal, 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 metal. Okay, it does still form a solid because these bonds here are fairly strong. We call them metallic bonding, but they keep us a solid room temperature. Let's switch over now to take a look at ionic compounds. Ionic compounds, we already saw the difference in electronegativity is large enough. So essentially what's going to happen here is for an ionic compound, the metals lose electrons. The terminology is oxidize. Metals lose electrons. I'm just going to emphasize that these ones here are transferred to nonmetals. And basically in doing that, the metal forms a cation and then we get an anion. So in this case here, imagine taking sodium and taking chlorine. I do have the numbers in front of me now. So sodium, first thing you check is the electronegativity. The difference is 0.9. Chlorine has a difference of 3.2. Again, aside from that average electronegativity where I need those actual numbers here, I just look at the difference. Sodium comes in with 1 valence electron. Chlorine is coming in with 7 valence electrons. It's the unpaired electrons that do the bonding. What we want to do here is the tug of war between these two. So if I go big number minus small number here, I'm getting 2.3. That's bigger than that rough 1.8 that we had. Seeing as I had it up above here, I can even calculate the average. The average would have been 0.9 plus 3.2 divided by 2. 0.9 plus 3.2 divided by 2 puts me on the average of 2.1. So if I have an average of 2.1 and my difference is 2.3, I can look on my triangular bonding diagram. My average was 2.1 and my difference is 2.3. That puts us very nicely in the ionic case. Again, if it's anything bigger than 1.8, pretty much it's going to be ionic. So what's going to happen here is these guys collide. The electronegativity says they potentially could have shared these electrons. But we find that chlorine is more of a bully. Chlorine pulls harder than that 1.8. It actually pulls so hard that it actually completely pulls this electron over to chlorine side. We end up with sodium having lost an electron. It's now positive. And then the chlorine already had 7 out of its 8 valence electrons. It's a tiny radius. Having stolen sodium's electron, it now has a full shell. It's now stable, and it's now taking on a negative charge. This becomes what's called a formula unit. It's sort of like an empirical formula. We know that by ratio in the formula, right, we just say NaCl. In reality, it's never so simple as just one single sodium, one single chlorine. It's actually that repeating pattern of positives and negatives. So in some sense, what I'm saying is these guys here are greedy. If we imagine the sodiums here are plus, although every sodium plus already has a chlorine neighbor, a Cl minus as a neighbor, what's going to happen is because opposite charges attract, although this is my formula unit, that is my building block, this positive is going to surround itself with as many negatives around it as possible. And likewise with the negative, surround itself with as many positives around it as possible. This structure here we end up calling a lattice, and this ends up repeating in 3D. So basically it just sort of repeats positive, negative all over. Okay, so make a note to yourself, all ionic compounds. We looked at just one transfer between one sodium and one chlorine. All ionic compounds, they form crystal lattices. The word crystal just means like nicely ordered, nicely packed together. But it's the word lattice here, which is that notion of it's a repeating positive and negative. And that's just because opposite charges like counterbalancing each other. Because ionic bonds end up forming this entire gigantic structure, we saw in chapter 3, it's really hard to melt. It's solid room temperature because you're having to come in and destroy every single one of these bonds here. That's why typically they're going to be solids at room temperature and really high melting points, just like metallic bonding was. In this case here, your ionic bond is your electrostatic attraction. Who's the positive and who's the negative? This time the attraction is going to be between the positive cation and the negative anion, because we have a full electron transfer here. Maybe I should write that down. An ionic bond is that Coulomb attraction. I've just been calling it an electrostatic attraction, positive negative attraction. But this time it very well is between your cations, the metal part that's actually taken a full positive, and anions. This time there are no delocalized electrons. Yes, we still have some background interaction with the positive centers also like the negatives, but it sort of is dominated over by the full positive one and full negative one between the metal and the non-metal. So we're going to use that difference of electronegativity of about 1.8 to define ionic, and generally it is metals fighting against non-metals that are large enough. That's why we can use the simplification metals and non-metals for ionic. One thing I want you to just take note of here is if you look at the data booklet, although we look at this and we say, yeah, sodium here is a big radius, chlorine here is same row but smaller radius, of course sodium would lose its electrons, a full shell, all that is true. But if you look at some of the ionization energies, sodium's ionization energy is still some like 500 kilojoules or so. That's not an easy number for sodium to deal with. So if sodium were just say, hey, pay 500 for me to give up the electron, it may not necessarily want to do this. Fortunately, in doing so, in being stabilized and getting that full shell, it ends up bringing the number a little bit back downwards. So it ends up paying me back a little bit. So I don't actually have to, just pay that money up front. For your ionic compounds here, because they are Coulomb attractions between positive and negative, in general, let's take, so far I've done sodium, like Na plus with Cl minus, those are on the same row. What if we went down to below sodium, potassium, I think cesium's coming up next here. We know that the radius increase is going downwards. What do you think is going to happen to the strength of the ionic bond? Right? So we're still thinking Coulomb here, F is equal to kq over r squared. In terms of charges, they're similar. In terms of charges, they're all +1, -1, even their z effective is the same. But this time, as I go downwards, we end up having larger radius because we have more shells. Right? Don't use z effective to explain going downwards. If I happen to have bigger radius, the force of attraction between positive and negative is weaker. So in this case here, we actually see melting point decreases. And it's because the ionic is weaker with larger distance. Right. So you see that those principles in chapter 3, a Coulomb attraction, this sort of kq r squared, that ratio comes back again and again. Right. So that's pretty much what I want you to know for ionic compounds for now. The charges are held tightly in the solid, so they're not conductive, but upon dissolving in water, when the charges can start swimming around freely, definitely going to be conductive. We'll end off here with our last type of bonding here, which is covalent. Again, they could be uneven or even. In this case here, we refer to electrons are shared. Typically, it is going to be between nonmetals. Okay. With similar, that's the more important thing, right? So the tug of war is fairly even, and they generally happen to have higher electronegativity as well. Between nonmetals with similar and generally higher electronegativity. That's not super important. If I have electronegativity of 1 and electronegativity of 1.5, that also would be covalent, but in that case there would be in that metal region there. So just to explain to you what is a covalent bond then, so let's take our fluorine example. Fluorines themselves, they have a bunch of electrons already. They're going to collide, so it's going to be the outer shells, the unpaired electrons that might end up doing the bonding. You check the electronegativity. Fluorine is always the highest. The closer to fluorine you are is going to be higher. The difference here is going to be 0. So not only are they similar, that was the more important point. Okay, the tug of war is fairly even. They also happen to be higher because they happen to be nonmetals. So in that case there, nobody really wins these electrons. They're going to actually hang out together. In tomorrow's lesson, we're going to come back and draw these using Lewis models. So we're going to draw a stick for a bond. One stick means a single bond. A single bond is 2 electrons. Those 2 electrons represent our negative charges. Those 2 electrons are sort of stuck in between the 2 centers because a covalent bond is the positive bit is the fluorine nuclei is attracted. It's trying to hold these electrons, positive likes negative. They don't want to get too close or else the electrons will repel and the positive will repel as well, but there's going to be a compromise where we end up getting a covalent bond length. That's the bond length of a single bond between 2 fluorines. So what is a covalent bond? A covalent bond, you can equally well call it an electrostatic attraction. Just getting you familiar with the language here, it's a Coulomb attraction between, again, we're back to those positive nuclei, just like we had in the metallic bonding case, and your shared electrons. Not delocalized, these electrons are sort of stuck in place, and they're sort of stuck holding the two fluorine neighbors together. Because there is no electron transfer, and these guys here are going to be individual molecules. Or molecular is another way of saying that. Individual molecules. So when you write, oh, F2 is a diatomic here, you write F bonded to F, that's all there is. It doesn't actually end up forming a lattice. We don't have those positive and negative interactions. I don't want to form a repeating pattern. If I'm even managing to cool it down fluorine into a solid state here, sure, the particles may be right here in place, but what I want to show you in this picture here is they are individual molecules. They're individual groupings. The intermolecular forces we'll see in a later lesson. They have those weak London forces, which is why these guys here are typically, in this case here, because in between we have very weak London forces. So these ones here are typically going to be gaseous at room temperature. Another way of saying that is you can say they have relatively low melting point, boiling point. They're individual. Well, you're just coming along and you're just breaking the odd London force here and there. They're already weak anyways. We talked about the London force getting stronger. So let's say going downwards for iodine. Iodine has way more electrons, right? But because they're individual molecules, it's still nowhere in comparison to how strong an ionic bond is or metallic bond is. But iodine here relatively has way more protons, comes with way more electrons, so way more attractions means the London forces are even stronger. That actually keeps iodine a solid, whereas fluorine is actually gaseous. So weaker, they're individual. These ones definitely don't form charges, so they're non-conductive. So I just wanted to introduce to you the main types of bonding, show you that ionic and covalent are two ends of a spectrum, but we can be anywhere in between. That's actually the only mention we're going to do for ionic bonds. We're going to spend the entire rest of the chapter just looking mainly at covalent because they're much more interesting. Right? So if you have any questions, just let me know. Thanks, guys.